Word. Okay, great. Thank you everyone for joining us for today's AMY seminar. Today's speaker is Malena Español. She's a professor at the Arizona State University. Her research, as I'm sure she'll tell us more about, is in inverse problems and image processing. And thank you, Malena, for being today's speaker. Take it away.
Okay, thanks. Thanks for the invitation. I have like two presentations because Jorge asked me to talk about my career a little bit at the beginning. So I'll start there. Let me share. Okay. Control. Okay, so let me start by, well, this is my from Buenos Aires, Argentina to Phoenix, Arizona, where I am, but everything in between. So let me, say that I was born in Buenos Aires, Argentina. I'm coming from, I'm a first generation college graduate. But yes, I am from a big city, and so I did my undergraduate there. I was kind of lost at some point, so I did a little bit of actuarial science, and I got an internship as an actuarial assistant. So I did I always knew that I wanted to do apply math. So everything I have done is, try to solve real life problems all the time. So I did kind of it's called so I did what is called licenciatura, which is a kind of a undergrad and master program at the same time. So I did I would say it's kind of an honors thesis about modeling Belousov-Zhabotinsky reaction. This is really system of ODEs, but the idea here is to model this and see they actually keep oscillating. So these are chemical reactions that keep oscillating and they don't stabilize. So I graduated from the University of Buenos Aires in a program that was really applied math. So I had, probability classes, statistics, optimization, numerical methods, everything at the undergraduate level. So I have to, I'm a very proud student from the University of Buenos Aires. I felt that the program, or now I value that program very much. So here I just to give you a flavor of things that I did during my my internship while I was still studying in undergrad, and this was trying to build give a price to health insurance policies in Argentina, and we were using statistics from the US to try to get some numbers from Argentina, but basically we were doing kind of a care fitting problem. Sorry, I won't go to the details because I kind of want to give you a flavor of things that I have done in my whole career. This is really kind of talking to graduate students or undergrads, but okay, maybe for postdocs and faculty is also useful. I don't know. So at some point, I moved to the States. Really was this, my husband wanted to study in the US, and he got accepted to do operations research at MIT. So I follow him. So I will say that I follow my lab. Then at the end, at some point, he started following me. So it's, this is a good partnership. But this is really the reason I came to the US. So I went to Tufts University to do a PhD. Here I have a picture with my PhD advisor, Misha Kilmer, the day that I defended. And I knew that I wanted to do applied math. It wasn't sure exactly which area, but she brought me into her research world, and I started working in image processing, numerical linear algebra. So I will say, if I have to say that I'm expert in something, I will say I'm an expert in numerical linear algebra. So just to comment things that I think were useful in my career. So one summer during grad school, I went to work with Gabriel Krayman. And let me just put a date, but this was 2007 when I worked with him. He was doing a lot of machine learning before people were doing a lot of machine learning like these days. And everything I learned about machine learning was from him. And it was during this summer. And the problem here was object recognition. So because he works in computational neuroscience. And again, I mentioned things, if at some point someone wants to know more or whatever, you can always reach me via email. I always say that I am an email away. So another thing that I did while I was a graduate student, and I really encourage graduate students to, maybe not the last summer when you really need to graduate, or, but, at the beginning of the graduate school, if you can go, spend summer in industry or a national lab or whatever, just getting out of your own institution and learn what other people are doing. So I did one summer, I went to MathWorks, which is in the, it's very close to Boston. And I worked there with Pat Cullian. And, if you do so I kind of work in this ILU function, MATLAB Beten function. And I learned tons of, how software development works. How do you design software that are going to be used for many people, right? In general, we create this code that we know, the input, it's for yourself, but it's a different story when you do software for the world. So this was a great experience. So after grad school, I went to Caltech, where I changed gears and I joined the group of Michael Ortiz. And this group is about computational solid mechanics, trying to understand materials and learn how to do simulations, accurate, efficiently. And my project was understanding the method that is called the quasi-continuum method. And the idea is that, here you have a material, maybe you deform it with a nano indenter, so you are going to deform the material at the atomistic level, but you couldn't do simulations, full molecular dynamics simulations when you have, a large amount of atoms. So this method, the idea is that, you kind of have an atomistic, or the physics at the atomistic level close to the nano indenter, or where things are going to deform, and then treat the rest as a continuum. So great experience. And I changed gears. I learned tons about materials. And then I went to the University of Akron, where there was a large, I would say, group of faculty working in material science or modeling material science. So there I started working in the modeling of 2D materials. Here, if you have two layers of graphene and you rotate them, then you start seeing these patterns that are called moire patterns. And we were trying to, I work with Dimitri Golovati and Pat Wilber there, and trying to create models, the atomistic model that we can upscale and get continuum models. But there, related to this seminar, I work on a project that I will tell you a little bit. I thought of making it also part of the whole, the main presentation about research, but I kept it in part of this experience or part of my career. But I was assistant professor there. I got tenure. I got associate professor and then tenure. But then I know. Okay, so before before telling you about how I got to ASU, I'll tell you a little bit about this problem medical imaging. So this is Chiari malformation. There was a center about Chiari in the University of Akron, where they were trying to understand this disease, which basically is defined as this the herniation of the cerebellum. So really the definition, at least a few years, maybe it's still the same definition, but if this deformation here of the cerebellum was larger than 2 millimeters, then it's like, oh, you are a Chiari patient. Even if you didn't have any symptoms, right? And maybe you went to the doctor because you fall, and then they did an MRI, and then suddenly they saw that you have this herniation here, they will say, oh, you know, you have Chiari. So this institute wanted to understand this disease from different point of views. They have mechanical engineers. They reach out to me as a mathematician to see what I could do. There are psychologists involved, you know, trying to again understand, you know, the disease from different approaches. And here, I, you know, kind of went back to what I knew about machine learning that I learned during graduate school. And I thought, okay, this is what I do. This is the, you know, what I knew, and I thought I could do something similar to what I learned during that summer. So here, the information that we have is that we have, you know, MRI images. That's the information. And, you know, I didn't talk about the object recognition. So this slide is kind of translating those ideas to this case, right? Where we have MRI images corresponding to, you know, normal patients, and then patients who have Chiari. And this is kind of one of the, you know, classification approaches where you try to find, so if you think about just data in the plane, you try to find a line that separates them. So if you have a new patient, you know, you use this line. This line is really the mathematical model that classifies. So if you have a new patient, you know, depending if it's on the right, and these are the, I would say these are the normal patients, then you would say, well, you don't have Chiari. But if you have, you know, if your MRI or your data is on this side, then you have Chiari, right? So we were trying to you know, do this classification model, but with the hope that we will learn something about the disease. Now, working with MRI data, you know, these are large, you know, large scale data sets. So instead, what we did was to, you know, this is very small, but we kind of do a feature extraction in some sense, in the sense that instead of using the whole MRI image as input data, we, you know, some radiograph people who do, well, doctors did some measurements before in previous papers. So I work with people who have done that before. So we use these measurements that they thought they were important, right? So here there are different lengths, you know, sizes of different parts of the brain, different angles that somehow might matter. And those were actually the features. So we you know, when I think about, oops, let me reduce it more. No, wait. I'm going the other way. So instead of having, you know, the data or these points are just 2 dimensions, or, you know, million of dimensions, if you use all the images, here we have only 19 features. Okay, so you can think that you are in this space of 19 dimensions, and then we were trying to create this hyperplane that separates them. And what we learned is that here there were features that were relevant for this classification. And actually they were on the other side of the brain, right? So here the cerebellum and this herniation is on the right. And we learned that the classification really, the features that were really more relevant were on the front of the brain. And this, of course, there were already some hypotheses that it is related to the development of the brain and so on. So, but this was, we published a paper with these results. Okay, and if you have more questions, of course, you can ask me. So after the University of Akron 5 years ago, I moved to Arizona State University as a assistant professor, and there I worked on different problems, and I kind of came back to more inverse problems, imaging applications, and I will tell you a little bit about that. Let me see. Okay, so I'm going to use just this slide. So I still work in materials. If you have questions in this modeling of 2D materials, but really I will say most of my research projects and most of my students, PhD students, are working on these projects now. So here I work for a little bit in this problem that is the active illumination system. This is if you have an object and you should, or you project. So here we have a projector where we can really define, so you can think about like having a grid and you can kind of turn on and off certain lights. So you can really design the pattern that you are going to project. So you create a pattern, you project, and you take a picture. You create another pattern, you project, and you get another picture. So from the information, from that information, knowing which pattern you project and the picture that you got, we were trying to understand how the light behaves in this particular object. And the idea here is to use it for virtual reality, right? So if you know how the light behaves, let's say in your face, right? Then you are, I don't know, play, in a video game or something, and then you can make it as realistic as, as possible using the way that you learn how the light behaves. A different project that I work on is this X-ray radiography. Here we have an object. We shoot it with high energy X-rays. And because these are high energy X-rays, you somehow need to stop them to see something. So you have what is called a scintillator. And here we have a camera that captures what is happening in the scintillator. So the inverse problem here, or what we want to solve, is that from this data, from these images, we want to reconstruct the density of this object. Okay, so again, an inverse problem in the sense that from certain kind of data, we want to, infer some other information, right? So in this previous one, from these images, we wanted to see how the light behaves in this object. Here, from these images, we want the density of this object. And today I'm going to talk about this problem. So maybe, well, I'll introduce it briefly here, but this is another inverse problem. This is called the electrical impedance tomography problem. So here we have the body, and we put electrodes around the body, and then we have a, we send some current and measure some voltages, and from that information, we want to reconstruct an image of what is happening inside. And that we can do, well, I'll talk more, but what I want to emphasize here is that these are all inverse problems, right? Again, from data, we want to create either some images or get some parameters. So the models look more or less like this, okay? but because the data has noise, we have to do regularization and use a lot of techniques related to inverse problems. But okay, so I leave it there. This is something that I do. Let me see. Okay, so let me change to this presentation and talk more about this electrical impedance tomography problem. So let me start by saying how we started working on this project. This was an REU, a research experience for undergrads. I will say, now I don't remember, 2 or 3 summers ago. So here I am with the undergrad students where I gave, so here, well, I am here. This is actually Mason Manning, and he was a PhD student at ISU, but he was the TA. So I gave the students, this project about electrical impedance tomography, thinking that they will, learn the main ingredients of inverse problems, like what is an inverse problem, how you solve inverse problems. And then Mason really pushed to do a machine learning approach. And then I was working with Rosalind Sadleir, who is an engineer and has a lab. She creates the, EIT, the electrical impedance tomography systems. So this is kind of a picture in her lab, a system where we can just test things. And Jacob Roarty is one of my PhD students that I brought to this project, because the project continued after the summer. I mean, continue for a whole year. Okay, so as I mentioned, this is about EIT. I mentioned how this the system works, right? We put electrodes around the body, and let me say that this really works because the different organs inside the body, the current behaves differently in the different organs, right? So what we reconstruct is really an image of how the current behaves inside. Okay, so as it says here, it's a low-cost, portable, non-invasive imaging system. So we can really use it to monitor continuously, something that we cannot do with MRI or CT. So it's really a very nice technology. The definition of the images, as I will show you, are not that great. But again, we can have this continuous monitoring of the lungs, of the heart, or what is happening inside the body. So it's really, there's a lot of work that we can do here, and it's needed. It has tons of different applications, right? So I mentioned you a few, but here people use, the vets use it for animals. Here, there's this paper that also can help in the early detection of breast cancer. This is some other innovative applications, also trying to see if, just with the images of the reconstruction, you could see what is the movement of a hand. And this is, some applications. Anyway. So, of course, there is math behind that. We need to describe all the physics of this system, right? How the current behaves and so on. So that is described by this equation here. And of course, we have the equations at the boundary that defines or describes, what we are sending, right? So we have the currents that we are sending defined really by this function G. We are measuring the voltages, and this is defined by this function D. In principle, you can think about, the forward model where, the forward model, you assume that you know your system, let's say inside the body. So you know this sigma here, and you have a, this PD, and you can solve it. And when you solve it, you can obtain what is this mu at the boundary. In the inverse problem is the opposite, right? So what we know is this current, okay? And this voltages is what we measure, okay? And we don't know the sigma, right? So now we have this equation that has a component here that is unknown. But we know what current we send. We knew that in the forward problem also. But now this, what the voltages at the voltages are at the boundary, this is measured data. Okay, and from this measured data, what we want is to reconstruct this sigma here, that is the conductivity inside the body. Okay. One way, using all we know about inverse problems, what we would like is to pose this minimization problem. This is one approach where we have this model, right, that depends on the sigma. Okay. Then these are the measured data. Okay, so what we like is to really find the values of sigmas. Okay, that will give us a PDE that it will predict. It could predict what is the voltage at the boundary. Okay, so this, in some sense, again, solving PDEs will give us what is the voltage at the boundary. On the other hand, we have the voltage the measured voltages, right? This is an inverse problem. We might have measured voltages that have several sigmas, right? Several conductivities that could give us that voltage. So it's an inverse problem. It has several solutions. And then, so to guide this minimization problem, we add a regularization that says, well, I don't want any conductivity. I want certain type of conductivity, right? So that's the role of the regularization term here. Of course, you could imagine that solving this problem is very costly. So first, it is a non-linear problem. So one way to solve it is linearizing. So you need to, when you linearize, you need to, find the gradient of this function. So there is a lot of work here to solve this problem. It's finding the Jacobian that is involved, and then solving these PDEs and so on. So what we propose is to do a machine learning approach. So let me say a little bit about the protocol, because this is how we also get the data. So, and let me also mention two things, or mention one thing, which is that we were particularly interested in a EIT system where we might not be able to put electrodes all around the body and only in part of it. Okay, so so here I'm going to talk about two EIT systems. One that has 16 electrodes, right? So we are putting electrodes all around. So we do pairs where we send the current, and then we use pairs to measure the voltages, right? So we are sending here certain current between these two, and then we are measuring the voltages in these pairs, and then now we switch. We now send current through these two, through this pair, and then measure the voltages in the rest of the pairs, and so on, right? So we are moving and sending current through different pairs and measuring the voltages, right? So we want to see how the body is reacting, right? So we measure and get data from the others. We are going to do something similar when we have only 8 electrodes, right? So still using pairs, and at some point we are going to use, this electrode and this one, right? So it's a pair where there is a big region in between. I hope that's clear how we are going to collect data, right? I mean, we do have a specific protocol, and everything I'm going to say is, how things work for this protocol.
I have a question.
Yes.
So this data that you're collecting, all of these cycles is for one solve of your inverse problem or different solves of your inverse problem?
Good question. So here, this is for, this is how the system will work, but we are thinking that you have, let's say, one patient, right? One data set, or no, one sample, right? And then we do it, but then you might have several patients and you get data from, it's going to become clear in a second.
So even if it is one patient, for the same patient, you have first cycle, second cycle, up to 16 cycles, and all of that set is the data for that one patient that you use in one solve of your inverse problem. If you have multiple, you can stack them in columns, but all of that comes from is for one solve.
Yes. Yes, okay. If you think just about the inverse problem, yes, that will be your data. Yes, right, in the traditional way of thinking inverse problem, yes, you will do the whole protocol. That will be your right-hand side or your data, and then you will try to solve with that information. You will try to see how is the conductivity of that patient.
Okay, and is it and the result will change based on what kind of protocol is chosen, like how the data is being collected, or is it about the size of the system changes based on underdetermined, overdetermined, and square?
No, there is a lot of research had been done on what is the right protocol or what protocol gives you the most accurate data.
Okay, so there is literature out there.
Yes. Okay. But good questions, Rana. Yeah.
Thank you.
Okay, so here, right? So yeah, as exactly what you were saying, right? Here we put the input. Okay, it's going to be all the voltages of the whole protocol, right? All going through all the cycles. Okay. Then, okay, here we are going to use a neural network that has only 3 layers. And then the output, okay, let me go to, sorry, I'm going to try, okay, maybe to explain here. In this particular case of how we, trying to understand and, and learn if this methodology could work or, applying neural networks could work. Here I have, I want to tell you how I got how the output looks, right? So here, what we want as an output, it will be, we want an image, right? But because we are solving PDs, here we have a, a grid, the triangulation. And of course, we are going to assume that the conductivity in each element, triangle, is constant. And that value in each element is what is going to be part of our output. Okay, so here, right, so if we have, let's say, 576 elements, what we have here is the conductivity in each element. Okay, once we have that, we can have the image. Okay, but things to emphasize, this right here depends on the mesh size, right? So we are going to, if you think about different patients, kind of we have the same geometry, the same number of elements, and so on, right? So
quick question.
Yes.
So this mesh size of your output also corresponds with the mesh size of your forward operator, like how you define that, like how that is discretized?
That's a good question. That's a good question. No.
Okay.
I think, no, the idea is that we use, this is related to how we define or simulate problems when we want to solve this EIT problem, even in the traditional way, right? In the sense that, in principle, this should be real data that you are measuring with the patient, right? In reality, we are simulating data.
Right.
To simulate data, what you want is to use a very fine mesh
Okay.
to have as accurate result as possible to get this data, because again,
Right.
it should be very accurate because it should simulate reality, right? But then when you are solving, testing your methods, the mesh that you use to solve this PD should be coarser. Okay, that is to not commit inverse crimes.
So that doesn't create a problem when you're training and learning, like your training data is on from a higher, like fine mesh, and you're training on a coarse mesh,
Mm-hmm.
and simulated data is on fine mesh?
No, so again, this no, let me think. That's a good question. So that's a good question. So I might be right. So for this problem in particular that we want to compare with the real, okay. Two things. Thanks for pointing this out. What I just mentioned is, again, I'm thinking when we solve these inverse problems, or everything that we should do. Now, that generates complications, right, of using different grids when I'm trying to do now this machine learning approach, right? So, yes. So
Yes,
for
sorry.
the machine learning, yes. So I think for the machine learning, we are using the same grid. Mm-hmm.
Okay.
But
Yeah, that would make more sense.
Yeah, but it is of course related to we want to compare and know how we are performing.
Right.
Otherwise, if you use different grids, then you need to do some interpolation.
Correct.
Yes. So
yeah,
this
that's
is
additional step, right?
right. So this is just to keep things simple.
Sure. Okay. Thank you.
But it's true that we might be doing, in some sense, some inverse crimes there. But I'm going to show you. I'm going to show you that we have applied this to real data. So our testing really is in real data. So we have a good test.
That's great.
Okay, so okay, so I hope this part is clear. So then the only difference when we have, half of the number of electrodes, then here the data will change, right? I have to say that we did a small transfer learning, in the sense that we did some learning here with a whole full array, and then we use some of what we learned there for this to learn this to train this neural network. Yes, question, Julio.
Okay. I have one question. These grids are created for each patient. I mean, the model needs to be trained for each patient and retrained for another patient, or there is like some matchup or some template or something.
So the hope is to design something that is independent of the patients, but there are many issues. And one I will point out that the geometry is an issue, something that it matters, but we are all different, right? So so that is an issue, right? So there are assumptions, you might get certain results, Also, you know, we talk about patients, right? But we are at the beginning of this, because right now, let me move on and show you a few things. I hope I answer questions, showing you a few more things. Let me move on a little bit. Yeah. So here, for example, right? So the training, so the first thing that we did, again, we are just trying to simplify many things, right? So right now, what we did to see if this is working, we have this circular domain. We put at random what will be anomalies. Okay, but the first observation that I want to mention is that there is no nothing here really looks like a body, right? So even though, you know, we are talking about patients and so on, we are far away from making this useful, I would say, right? So we are at the very beginning of seeing how this could work. Again, there is no organs here, right? We have a domain that has nothing, and we just put something that I like to think about an anomaly. Okay, so we put different anomalies, you know, different sizes in different places. We put, you know, 1, and then we put 2 again at random places. We are using the same grid. And then we, you know, we created the data, you know, solving the PDEs for each of these cases and getting the voltages. Okay. Okay, so here some results. This is what we would like to see that we recover, right? So we have the voltages, and we want to see if we can recover these, you know, conductivities. This is using T-cone of regularization. Okay, I mean, okay, give us more or less some information. This is using the full array. This is another inverse problem technique, right? We are using truncating SVD here. Okay, so the results are not that great, and this is using the neural network, right? So really the results are pretty good. Here, this is using a half array. Okay, so the information and the data is only obtained in this part of the body. Here, okay, maybe this, you know, this is using T-cone again, truncating SVD, and this is the neural network. So here, if, you know, the anomaly is close to the electrodes, you could kind of see that you could still maybe reconstruct or, you know where it is. But for example, here where the anomaly is further from the electrodes, well, in these traditional methods, we couldn't reconstruct it at all, and this neural network does a good job. Now we tested with real data, right? How did we obtain that? So here we have a tank where we put some salt and water, and then we put prompts that were basically cylinders, one that was a metal and one was a plastic. And this we did by hand, right? So I have a cylinder that I will put on the water, and then, you know, more or less know where I was putting. So this is a very, I don't know, rustic. I don't know what's the right word here. But with the training that we did with the simulated data, okay, with that network that we learned with that simulated data, we use that model to, in this case, right? So we have the voltages, okay, and we just gave those voltages, and with those voltages, we try to reconstruct, okay? And it did a good job here in the metal. In the plastic, well, maybe not so much, okay? Let me say something that might not be clear here, but this is half array, right? So here the electrodes are here, and although it might be confusing because here we have electrodes everywhere. Actually, we have electrodes only in one part. Okay. Now, we now say, okay, but this, you know, our tank is not complete. It's not really circular, right? It has kind of elliptic form or ellipsoid form. Elliptic. I don't know what's the right word. So we did everything again, but now using a different geometry, right, for the domain. Do all the simulations, the training again, right? So which means that we simulated data again with this domain. And then we see that all the results improve, okay? Well, here we didn't have that so much in a problem with the simulated data, so let me go directly here. But we see now that if we have a better domain, okay, the domain that is aligned with, you know, with the real domain, we get way better results, okay? So, but there is an example where we are simulating using, you know, certain grid, but this is real data, okay? So let me just, you know, finish there saying this is a published paper. You can go and read more details if you want there. What we are doing right now is, well, we want to extend this to 3D, but for more realistic cases. So we are getting, you know, data where we do have the lungs, and we want to start doing something more realistic. So we are doing a model that is a 3D, but also, you know, putting the organs there, and then we will see what happens if we use this kind of neural network or others. Okay, so this is our current work. So yeah, let me know if you have questions.
Great. Thank you so much, Malena. Let's give them a round of applause. If you have any questions, feel free to unmute or put them in the chat. It looks like Ratna might have another question.
Yes, I have another question.